We'll get started. So the first announcement, the midterm one is going to be next week on Wednesday. I hope all of you are preparing hard and burning midnight oil to prepare for the midterm one. Today we are going to talk about Lagrange multiplier theorem. So we've talked about unconstrained optimization, necessary and sufficient condition. Then we talked about optimization over convex sets, necessary and sufficient condition. So by the principle of mathematical induction, today we want to solve optimization problem over constraints, and we want to talk about necessary and sufficient conditions. So what is the setting here? I want to minimize the function f of x such that h of x equals to 0. And when I write h of x equals to 0, so f is still a function from Rn to R, but h here is a function from Rn to Rm, and I can as well write it as h1 of x, h2 of x, hm of x equals to 0. So I have like m functions of x, and I want all of them to be equal to 0. So an example of this would be, I want to minimize f of x such that x1 square plus x2 square equals to 1. Okay, so this is my h of x, or maybe I'll write it as minus 1 equals to 0. So this is my h of x. So what I'm doing here is minimizing the function f of x over a unit circle. Is this set a convex set? H of x equals to 0? Just a unit circle? No, right? So I pick any 2 points on this unit circle. I draw a line. If you pick any point here, h of x is not equal to 0. So not a convex set. Any question? Okay. So we are slowly moving towards optimization problems over non-convex sets. But here the non-convex sets appear as equality constraints, where you have a function of x and you want to make sure that the function of x is equal to 0, and you are minimizing the function over such a set. Okay. So the first thing I want to talk about is this notion of regularity. So x in Rn, h of x equals to 0 is a regular point if and only if. So this is the definition. Gradient of h1 of x, gradient of hm of x are linearly independent. This is equivalent to saying gradient of h of x is full rank. Okay, so let's look at this example again. This is my h of x. What is gradient of h of x? What is the gradient of this function?
Is it 2x1 plus 2x2?
Okay, that's the gradient. Is this a full rank matrix? So when is this matrix not a full rank matrix? When does this matrix, when is this matrix equals to 0? I mean, it's not a matrix, it's a vector right now. But when is this vector equals to 0? When x1 and x2 are both equal to 0, right? That's the origin. And origin is not part of the circle. So the notion of regularity is h of x is equal to 0. So I'm only looking at points on the circle, and I want to make sure that the gradient is not equal to 0. So this is because there is only one vector here. All we care about is that the gradient is not equal to 0. If I had multiple constraints, so for instance, let's look at another example. So I'm going to, okay, let's look at it in a bit. Okay, so do you all agree that this particular point, I mean this all points within this set h of x equals to 0 is a regular point because it satisfies this condition that gradient of hx is full rank or gradient of h1x to hmx are linearly independent. So all these vectors have to be linearly independent. In the case of a single vector, we don't want that vector to be identically 0 at any point within the set, within the constraint set. Okay, so let's look at an example where we have regular points and we have irregular points. So I have two constraints in R3. So let's say I'm looking at R3. In the first case, I have these two sets, two constraint sets. And I'm looking at this particular set. So this is my h1 of x equals to 0, h2 of x equals to 0, and this is my constraint set. So at this point, along this particular curve, my h of x is equal to 0. Yes.
Is that a line that is included in both surfaces?
It's I wouldn't call it a line, but it's definitely a curve.
Oh.
Yeah. Okay, so I have two surfaces, two curved surfaces, and now, so each of this surface is represented by h1 of x equals to 0 and h2 of x equals to 0. Wherever these two surfaces are intersecting, which is this particular curve, this curve lies on both the surfaces. It lies both on h1 of x equals to 0 and h2 of x equals to 0, and that's my constraint set h of x equals to 0. What's the gradient of h1 of x? How do I represent gradient of h1 of x? So I pick a point x here. This is my point x. What's the gradient of h1 of x? So it's outward normal. So a vector that points 90-degree away from this particular surface. So something like this. This is my gradient of h1 of x. What about gradient of h2 of x? So it has to point 90 degrees from the surface. That's my gradient of h2 of x. Are these linearly independent? They are pointing in different directions, so they are linearly independent, as a result of which this point is a regular point. So when will this point not be regular point? When the both vectors are pointing in the same direction. When will they be pointing in the same direction? When these two surfaces are just touching each other. So let's look at another example. So this is my h1 of x equals to 0. This is my h2 of x equals to 0. And this line is my h of x equals to 0. So this is the point where both these surfaces intersect. And in this case, let's say the gradient of h1 is pointing in this direction, and the gradient of h2 may be pointing in this direction. So they are not linearly independent, they are linearly dependent. So this vector is negative of the other vector. Okay, so that's also linear dependence. In this case, this is not a regular point. So not a regular point. So in what follows, for the foreseeable future, we are going to be considering situations where this is not the case and this is the case. Okay, so we'll only solve optimization problems where every point within the constraint set is a regular point, and we will not consider optimization problems where the points may be irregular. The thing is that with regular points, you can come up with beautiful algorithms. With irregular points, the algorithm becomes considerably harder to use. Any questions so far? Yes.
What does the regularity indicate? Like, does it indicate that one of the constraints is redundant?
It's not quite redundant, but it means that there is some sort of degeneracy, in the sense that so in general, when you have when your points are regular, it means that, so definitely if you have redundant constraints, then it won't be regular. So that's always the case. But you could have, for instance, you don't really have redundant constraints here. You just have a constraint 1 and constraint 2, and both of them seem to suggest that yeah, I don't know how else to say whether, yeah, in this case it's not really redundant constraints, but yet there is irregular points that are appearing in the constraint set. We'll talk about the proof of the necessary condition. So there you will see why this particular problem, why this condition creates a problem. But then I don't know what is a good way to think about it. I think I don't have a very good geometric picture beyond this particular setting where two surfaces are just touching each other, and then that creates irregularity in the constraint set. Any other question? Okay. So now that we have understood the notion of regularity, most of the times when you are solving a problem, you will mostly be encountering, if it's a real world problem, you will mostly be encountering situations of this type. Of course, when we talk about algorithms, when we talk about theory, we have to consider situations like these, but most of the time, these are the kind of problems that you will be encountering in your day-to-day situation. Now, if you have redundant constraints, you have already done some assignment problems where you had to remove redundant constraints, and you will end up doing removal of those redundant constraints in the future in order to make sure that your optimization algorithm converges to a reasonable solution. Okay. There's another thing I want to introduce, which is, remember, in the context of convex set, you could move in a direction and you will still remain within the convex set. In the case of Rn, you can move anywhere in the space. The problem in this particular situation, so let's say if I'm zooming in, I'm looking at, I have my eyes here and I'm looking in this particular direction, what I see is a constraint set that looks something like this. Okay, so this is my constraint set, h of x equals to 0. I'm at a point x. No matter what direction d I pick, I'm going to go outside the set. Okay. However, it's not very far away from the set itself. So for instance, if you're moving in this particular direction, you may have a very small error here. Okay, so you're still close to the curve, you're not far away from the curve, but you are not on the curve. Okay, so that's the important distinction to make in this particular situation where you have multiple curves and you're trying to optimize the function over such curves, wherein if you take a step in a specific direction, you may go outside the set, and that's something we have to be aware of, and we need to make sure that our algorithms don't go outside the set. I mean, it can go outside the set, but it has to converge to a point which is within the set, and those are the kind of algorithms we'll design eventually. So this leads me to the definition of first order feasible variations. So this is the set of, we'll denote it by V of x, and this is the set of D in Rn such that gradient of Hix transpose D equals to 0 for all I equals 1 to m. That's called first order feasible variations. This is the set of first order feasible variation. So set of first order feasible variations is given by this expression. So going back to this particular example, I have my gradient pointing in this direction and this direction, and the first order feasible variation is a gradient that is orthogonal to both of these. It's a direction orthogonal to both of these gradients, so it's moving in that direction. So going back to this picture, this is my gradient of h1 of x. This is my gradient of h2 of x. And you can think of this direction d, which is in a orthogonal to the plane that is spanned by the gradient, these two gradients. Okay, I'm not sure if the geometric picture is something you are able to visualize or not, but if you're not able to visualize it, please let me know right now so that I can come up with a better picture. So I have two vectors like this. I have two vectors that are like this. And my first order feasible direction is a vector that is going in this direction. Okay, so that's what this set V of x represents. Okay, wonderful. So now we are ready to introduce the necessary condition for optimality. So we talked about regular points, we talked about first order feasible variation. So this is the famous theorem, Lagrange multiplier theorem. So we have two functions, f, which is a smooth function from Rn to R. We have a function h, which is a function from Rn to Rm. This is also differentiable. And the Lagrange multiplier theorem says if x star is optimal, is a local minimum, and a regular point, then there exists lambda star in Rm. These are known as Lagrange multipliers such that gradient of fx star plus summation So this is the first order necessary condition for optimality. This is the second order necessary condition for optimality. Okay, so I want to fly a plane. I want to reach from Columbus to whatever is your favorite city. So let's say New York. So I want to reach Columbus. I want to go from Columbus to New York with minimum amount of fuel in a flight. And so the flight is, so I want to minimize the fuel consumption of the flight such that I have to be on the surface of the planet. Okay, I can't dig a tunnel and go through the planet, so I have to follow the curvature of the planet. So that's hx equals to 0 constraint. And what the Lagrange multiplier theorem says is, well, technically speaking, if you're on the surface of the planet, every vector is pointing right into the sky. So all the derivatives of h of x equals to 0 is pointing into the sky. So those are non-zero vectors, as a result of which all points are regular. So what the Lagrange multiplier theorem says is, if you look at the derivative of the gradient of the fuel consumption along the path, so we want to optimize the path. So so in that particular situation, the derivative would be linear combination of the derivative of hi of x star, which is a constraint. Okay. You can also think of it as, remember I have these two vectors, gradient of h1 and h2. So I can draw a plane. I can draw a plane which contains these two vectors, and my gradient of f actually lies within this plane. So this is what my gradient of fx star is going to look like. Okay. So that's another way, geometric way to look at the first order necessary condition for optimality. So whatever is the plane spanned by gradient of hi, the gradient of f must lie within that particular plane. Remember that these lambda I star could be equal to 0. So lambda star is supposed to be in Rm. So some of these lambda I star could be 0, even though the gradient of hi need not be 0. Okay, so that's the Lagrange multiplier theorem. We'll prove this theorem in the next class, but I'll go through a couple of examples just to show you what it means for Lagrange multiplier theorem to hold. Okay. Okay, so let's try to solve the following problem. I want to minimize x1 plus x2 plus x3 such that x1 square plus x2 square plus x3 square equals to 3. So I'm again looking at the surface of a sphere in 3 dimensions. The radius of that surface, the radius of that sphere is square root of 3. Okay, and I'm trying to optimize this sum of 3 variables over the specific sphere that we are considering. So all points are regular in this case. We can easily check. If you take the derivative of h of x, it's 2x1, 2x2, 2x3. They all cannot be identically 0 on the surface of the sphere, so therefore all points are regular. What does x star and lambda star, what do they have to satisfy? So I have one constraint, so there will be only one Lagrange multiplier, m is equal to 1. So let's see, my gradient of fx star, what's the gradient of the function? The objective function? 1, 1, 1. What's gradient of h of x star? 2x1 star, 2x2 star, 2x3 star. So this Lagrange multiplier theorem says is x star is a local minimum and a regular point, then this particular statement has to hold. So what I get is 1, 1, 1 plus 2x1 star lambda star 2x2 star lambda star Okay, so my goal is to find x1 star, x2 star, x3 star. That's what I'm interested in. This lambda star is sort of a variable that appears out of nowhere here, and it should satisfy this particular condition. So I have gradient of fx star plus lambda star times h of x, gradient of hx star equals to 0. So I have 4 unknowns here, x1 star, x2 star, x3 star, and this lambda star appears to be the 4th unknown. But I only have 3 equations, so what should I do? I have 3 equations, 4 unknowns. Can I solve this problem?
Rewrite the constraints in terms of the other variable.
Okay, yeah, so that's a good point. So this constraint has not appeared so far here. So I'm going to add that constraint, x1 star square, x2 star square, x3 star square equals to 3. So now I have 4 equations and 4 unknowns. Okay, I can solve this 4 equations and 4 unknowns. How do I solve it? Let's see. I have x1 star is equal to minus 1 over 2 lambda star, x2 star equals minus 1 over 2 lambda star, x3 star equals minus 1 over 2 lambda star. Okay, so this one gave me these 3 equations. I'm going to substitute this into this expression. I get 1 over 4 lambda star square plus 1 over 4 lambda star square Okay, so now I have another trouble. I have 2 possible values of lambda star. It could be plus 1 over 2, it could be negative 1 over 2. Which one is the right answer? What do you think?
Maybe just whatever two, since it's a sphere, it can't be negative. Is that,
Lambda star cannot be negative?
yeah, is that possible?
No, lambda star can be anything in Rm.
Oh, yeah.
Yeah, it doesn't have to be positive. So lambda star equals to minus 1 over 2 is still a possible option. How do I know which one is the right option? Yeah.
I think it should be positive because when it's positive, then the x's are negative, and so we can minimize.
But we can't go by thinking. You are right. You are absolutely right. But we can't go by gut feeling and optimization. That's a slippery slope. You know, when we were.
Also, we know the x1 star, x2 star, and x3 star is equal to 1 minus 1 over 2 times lambda star.
Right. So once I pick a specific lambda star, I automatically get x1 star, x2 star, and x3 star. So I'll be able to solve the problem. The only problem is I don't know which lambda star is the right lambda star. Any other thoughts? What have we used so far? So what we have used so far is the first order necessary conditions for optimality. And where I'm stuck is I was able to solve everything correctly. So this is the first order necessary condition for optimality. I augmented it with the constraint. I get 4 equations, 4 unknowns. I tried to eliminate, because of this equality, I tried to eliminate x1 star, x2, x3 star. And I substituted the expression here. And I get 2 values of lambda star. So first order necessary condition for optimality has been exploited to its fullest. Now we can exploit the second order necessary condition for optimality and see what lambda star turns out to be correct. Okay, so what's gradient of fx star? Sorry, the second derivative of the function f. What's the second derivative of 0? So this is 0 plus lambda star. What's the second derivative of h of x star? So I have only one constraint here, so I is just equal to 1. What's the second derivative here? Yeah, 2i, perfect. 2, 0, 0, 0, 2, 0, 0, 0, 2. This needs to be non-negative for all d in Vx star. What value of lambda star can I pick so that this scalar is non-negative?
Pick 1/2.
Just take a positive 1/2, in which case this is a positive definite matrix, in which case this particular statement holds for all d in Rn, not just for Vx star. So I know that lambda star must be equal to 1/2, in which case, as somebody rightly pointed out, each of these x star would be a negative value, and that's the right answer. That's the optimal solution. Okay, well, I've made a claim here. By substituting lambda star equals to 1/2, I get x1 star equals to x2 star equals to x3 star equals to -1. Is this an optimal solution? What I did was I used first order necessary condition for optimality and second order necessary condition for optimality to identify these these four variables that satisfy both FONC. It satisfies this and it satisfies this. Can I conclude that this is an optimal solution? So when we were trying to minimize x cube over R in assignment number 2, question number 1, x star equals to 0 satisfied the first order necessary condition for optimality and second order necessary condition for optimality. But is 0 an optimal solution of x cube? Is it a local minimum of x cube? Not really, right? So we can't really conclude anything from here. All we have done is identified one candidate solution. And how do we ascertain whether this is indeed a solution or not? We need to look at sufficient conditions for optimality, right? So what's the sufficient condition for optimality in the context of this class of constrained optimization problem? So let's look into this. But is the approach clear? So we have this objective function, we have the constraint. We get so gradient of fx star equals to lambda I times this. This gives me n equations, and then h of x equals to 0 gives me m equations. So I have n equations here, m equations here. I have n plus m unknowns. So n unknowns are x star and m unknowns are lambda star, right? So I have n plus m equations, n plus m unknowns. Now we can solve the problem. And by going through the first order and second order conditions, I'm able to narrow down on the candidate optimal solutions. And now let's look at the sufficient condition. So x bar lambda bar is in Rn cross Rm, and it satisfies gradient fx bar plus summation I equals 1 to m lambda I bar gradient of hi x bar equals to 0. So that's looks very similar to this, and d transpose second derivative is strictly positive for all d in Vx bar, d not equals to 0. Then x bar is a local minima.
See ya.
So I wanted to optimize a function over a set of constraints such as h of x equals to 0. God came in my dreams and told me x bar and lambda bar. And now I need to figure out if this is the correct solution to the optimization problem that I had or not. So I quickly went back to MATLAB and I checked if this is true and if this is true. And if both these conditions are true, then x bar is a local minimum, guaranteed to be a local minimum. And as you can see here, this condition is satisfied because this is a positive definite matrix. So for all d not 0, this product is strictly positive. So the only difference that you can see in the necessary condition and sufficient condition is I don't require this x bar to be a regular point. I don't care about regularity in sufficient condition. This condition remains the same. This condition, the only other thing that I have added is d not equal to 0, and this has to be strictly positive. So with these two changes, what I get is a sufficient condition for optimality. Okay, and this allows us to establish that this is indeed the optimal solution to the problem that we were considering. Okay, any questions so far? Yes.
Why don't we just say the matrix is positive?
Yes, extremely good question. So why don't we just say that this particular matrix is positive definite? So the thing is, this matrix, this is of course a symmetric matrix, because what you are doing is you are adding a symmetric matrix with symmetric matrices multiplied by some number which could be positive or negative, right? So what you get is a symmetric matrix. Now in symmetric matrix, you could have some eigenvalues that are positive, some eigenvalues that are negative. All I care about is in the directions of first order feasible variations, it be positive definite. Only in that direction. In the other direction, it could be negative definite. That's fine, right? So if I'm going in the direction D, first order feasible variations directions, this should have positive eigenvalues. If I'm going in some other direction, not going in this direction, it could have negative, it could have positive, I don't care. Okay, in this case, it has positive eigenvalues in all directions. So our life becomes much easier. If it didn't have that condition, then it will be somewhat difficult to check. Yes?
So the positive definite matrix is actually a stricter constraint.
It's a much stricter constraint, yeah. So in exams, I'll give you situations where you have positive definite matrix, so it becomes easier to write the solution in like 2 minutes. But in life, you won't get positive definite matrices. Okay. Any other question? Okay. So you might be wondering that this term f plus lambda times h seems to be appearing in multiple places. So it must have a special name, special meaning. And you are right, the name is Lagrangian. Defined by L of x times x comma lambda, and this is f of x plus lambda transpose h of x, which is the same as f of x plus summation so Lagrangian is a function of x and lambda. Lambda is known as Lagrange multiplier. X is of course the variable. So L is a function from Rn cross Rm to R. Okay, so the first order necessary condition says gradient of x of gradient with respect to x of the Lagrangian is equal to 0. Second order necessary condition says d transpose right. So this is the first order necessary condition, that the derivative of Lagrangian with respect to x vanishes at x star and lambda star. And the second order necessary condition says that the second derivative of Lagrangian with respect to x when multiplied by d on both the sides is non-negative. Okay. Same thing can be said about the sufficient conditions as well. So this is gradient of Lagrangian equals to 0, and this is second derivative of Lagrangian is pre-multiplied by d is strictly greater than 0 for d not equal to 0. Wonderful. So let's look at what's the origin of this particular condition. So what exactly are we trying to do? What's the proof of Lagrange multiplier theorem? So I'm going to introduce the proof today, and then we'll complete the proof in the next class. We are not going to prove the sufficient condition. It's a much more complicated and involved proof, as complicated as this particular theorem. So I'm just going to do the necessary condition. I won't do the sufficient condition. And then I'll talk about KKT conditions in the next class, wherein, remember, here we have only considered equality constraint, h of x equals to 0. Not all situations will have equality constraints. Sometimes you have inequality constraints. So how do we solve problems with inequality constraints? So we'll talk about KKT conditions, which serves as the necessary conditions for optimality when you have both equality and inequality constraints. So those are things for the next class, but this class, let's try to figure out how exactly do you prove a result of this type? What is this lambda star? Where did this come from? Okay, so I'm going to introduce a function I'm going to define it as fk of x, f of x plus k over 2 norm of hx square plus alpha over 2 x minus x star square. So alpha is greater than 0 and k is a natural number. I'm going to define a set capital S x such that x minus x star less than equal to epsilon. And I'm going to define xk as argmin Okay. So remember, this is my surface h of x equals to 0. This is a point x star. It's a regular point, so the gradient of h of x, hi of x are all linearly independent at this particular point. Those are the two things given. X star is a local minimum and a regular point. This is x star and this is a local minimum and it's a regular point. I'm going to draw a sphere of radius epsilon around x star. Okay, I drew a sphere S around x star. The radius of the sphere is epsilon. It's a solid sphere, and I am going to minimize this function fk of x over the entire space. And let's say I get a point xk. That's the argument of this function fk of x over this set. So I have x1, I have x2, I have x3, I have xk plus 1, and so on. Okay, so for every k, I get a solution of this particular optimization problem. What do you think will happen as k goes to infinity? So at every point of time, I'm looking at the sphere, I'm constructing a function. For every k, I'm constructing a function, and I'm minimizing that particular function. And I'm letting k go to infinity. So I get a sequence of optimal solutions. What do you think is going to happen to that optimal solution? They'll be all?
All hx.
It will be on hx? Okay, so one of your friend says that eventually all of these xk will be on this particular surface. Why do you think that should be the case?
Because the weight is increasing.
So this particular term is increasing to infinity. For this term to be finite, this term must be equal to 0, right? As k goes to infinity, this term should go to 0. So technically speaking, you won't be on the surface, but you will be close to the surface. Okay. As k goes to infinity, this term, if it is non-zero, this one is going to blow up. So certainly if you are minimizing the function over this set, this term must go to 0 as k goes to infinity. Okay. But it's not very clear whether this term, the sequence xk, is going to converge to x star or not. Okay. So what I'm going to tell you in the next class is that this particular sequence, we can construct a convergent subsequence, and that subsequence is going to converge to x star. And then based on the first order, we look at the derivative of fk of x, and because it's going to be in the interior of the set S, the derivative will be 0 for k sufficiently large, and by looking at the derivative, we'll identify this term lambda I star in that process by taking appropriate limits. So those are the things we'll be talking about in the next class, but at least we got the intuition right, which is that when we construct the sequence is actually going to converge to x star eventually, and that will help us get to the first order necessary condition for optimality and second order necessary condition for optimality. So thank you so much, and we'll meet again in the next class.